For 70 years, the world's most famous bridge has been under constant attack from nature's destructive forces. Treacherous currents batter its foundation, fierce winds bend its towers, sea fog, laden with corrosive salt, eats away at its massive metal heart. With a tireless team relentlessly replacing the cracking concrete and rusting iron, the bridge stays one step ahead. But the worst is still to come. Quake that will dwarf the killer quakes of the last century. An earthquake that could put this bridge in pieces beneath the bay. In a race against time, San Francisco's Golden Gate Bridge is being rebuilt to withstand the most powerful force on Earth. Of all the forces of nature that San Francisco's structures face, earthquake is the ultimate destroyer. Deep inside the rock, an unimaginable force is building. When the pressure gets too much, the earth moves. In San Francisco, it's happened before, and it's going to happen again. Right now, the city and its famous bridge are staring down the barrel of a gun.
Our day is coming, and we're just racing against time to get that bridge retrofit so it can be saved forever.
The prediction is there is less than 35 years to save San Francisco's most beloved landmark.
Within next, I think 35 years, we'll have a really major quake.
Against this ticking clock, engineers are urgently retrofitting the bridge against the next expected major quake. 100 years ago, San Francisco was destroyed by a major 7.9 earthquake. The really serious news for the bridge is the next seismic event is forecast to be nearer and bigger than any of the original bridge designers could have imagined. To stand any chance of survival, the steel and concrete of the 70-year-old superstructure is undergoing a major overhaul.
We are retrofitting these structures for 8.3 on the Richter scale.
In a $400 million retrofit, they're strengthening and retuning its worn-out frame to face an 8.3 earthquake, bigger than anything in living memory. But even before the bridge existed, here at the Golden Gate Straits, the elements were conspiring against it ever becoming a reality. And it wasn't just the risk of earthquakes stalling the dream. The winds at the entrance to the bay are far too menacing. The cold, damp fog eats metal and creates evil working conditions. And the raging waters racing through the gate are way too wild to build a structure in. So with all these destructive elements stacked up against you, and the spectre of an earthquake always there, why on earth build a bridge? 1918, and San Francisco is a success story waiting to happen. But its location isn't helping. Being squeezed on a finger of land, surrounded by the bay to one side and the ocean to the other, is cramping the city's style. But beckoning at the end of the peninsula, across a treacherous 1-mile gap called the Golden Gate, there is opportunity for all. Here, in the unspoiled acres of Marin County, there is real estate, a workforce and untapped resources for the city folk to enjoy. It's a tempting land for a growing city. The ferry boats are fit to bursting. A bridge had to be built. January 1933, the construction challenge of the century finally kicks off. Build the longest bridge in the world with the tallest towers and the deepest foundations in just about the worst place in the country. It'll take 80,000 miles of cable, 11 lives, and an unprecedented series of construction firsts before the dream of Golden Gate became a reality. The first major battle against the elements is to build the colossal foundations for the South Tower. The pier is a structure the size of a football stadium, set 1,125 feet from the shore, deep in the raging waters of the gate.
It's approximately 500 feet deep, right under the Golden Gate Bridge, where the land is very narrow, that water is going to move very, very quickly.
As if to demonstrate how foolhardy the venture is, in the first year of construction, fogs, storms, and currents each take their toll on the building of the South Pier. It soon becomes the most cursed part of the bridge. The groundwork for the underwater foundations is prepared by divers, each descending from precariously anchored barges. This is a high-risk construction because the colliding currents at the gate are a potential death trap. As the tide turns and the seawater meets the bay runoff, water flows in two different directions at the same time. Millions of cubic feet of light fresh water fight to escape from the bay, while denser, cold Pacific saltwater forces its way in. Divers constantly struggle for control in the turmoil. The solution is as drastic as it is dynamic. Giant steel tubes are lowered to the seabed below, and dynamite is packed into them. Bit by bit, the team blast their way to the bedrock 100 foot below. Beneath the waves, the work progresses well. Above, it's a different story. It's too rough to use barges and floating equipment. The solution? An 1,100 foot jetty, big enough to get everything to and from the worksite. But here again, the elements rear their ugly head. Disaster strikes in August 1933. An outbound freighter 2,000 feet off course plows into the newly finished structure, wrecking the sturdy construction. The ship's captain is blinded and disorientated by the summer fog that came in without warning.
It can come in rather quickly, and when it's thick, I mean, you can't see anything. You're in the fog, there's a big ship, it's headed right at you. That's kind of scary.
2 months later, and the pier is rebuilt. But an October storm lashes at the newly reassembled timbers, ripping the deck away. Yet again, it's rebuilt, only to be hit on December the 14th by an even more violent storm. 5 months later, a new jetty is built, tough enough to take whatever is thrown at it. With the seabed blasted flat, enormous concrete blocks are lowered down and locked together to form an oval container, protected by an outer fender. 9.4 million gallons of water is pumped out of the fender, and a massive 130,000 cubic yards of concrete is poured in. Men, knee-deep in setting concrete, race against time to spread it out across the giant container, building a solid base up from the seabed. On January the 3rd, 1935, the pier, the largest ever constructed, reaches its final height, peaking 44 feet above high water. Already stacking up on the docks are the components for the next two most iconic achievements of the Golden Gate Bridge. 80,000 miles of wire for the record-breaking cables and 44,000 tons of structural steel destined to make the 746-foot towers the tallest and most graceful in the world. The next stage of this supreme construction achievement is to push the boundaries of engineering, result in a tragic series of deaths, and put the wildly driven man behind the world's ultimate bridge into an early grave. To push the limits of bridge building in the swirling currents, raging gales, and steel-eating fog of the Golden Gate was going to need some kind of an engineering genius. Only one man stepped up to the plate. A short German from Chicago with a giant ambition and an ego to match. On paper, Joseph Strauss, the driving force behind the building of the Golden Gate, was about as unsuitable as the wild, windy, earthquake-prone location. Strauss had never built a suspension bridge, didn't have an engineering degree, and yet he was suggesting building the biggest, most complex bridge in the world across the unforgiving Golden Gate. Still, at $23 million, his price is right, his vision undeniable, and he swiftly puts together a dream team to knock his plans into shape. His first recruit is renowned engineering professor Charles Ellis. A meticulous, conservative intellectual, Ellis gives the project the precision and credibility it lacks. Strauss then adds Leon Moisieff, hotshot designer of New York's Manhattan Bridge. Together, Moisieff and Ellis rewrite the rules of what is technically possible. Their crowning achievements, the two suspension towers, stand over 700 foot above water. Built to precision by the elite ironworkers, or bridgemen, as they like to be called. These men travel the world in search of elite construction jobs. At the Golden Gate, it was like bees to a honeypot. The components for the towers are fabricated in Pennsylvania and then transported by barge via the Panama Canal all the way up the coast to the bay. They're constructed from clusters of hollow cells fashioned from inch-thick steel plate. Each tower shaft was formed from a honeycomb of cells, 97 at the base, reducing in number to 21 as the towers rise up and narrow. These stepped-off towers are a design first. Shaped to support 75 million pounds of dead weight in the cables and roadway, and, if the bridge is loaded end-to-end with trucks, an extra 9.5 million pounds of live weight. The towers are the masterpieces that define the Golden Gate Bridge. Inside and outside each tower run 23 miles of ladders, reminding us with each rung that this monstrous construction was built by men, step by step.
It was our ironworkers of the same local I'm in, 377. It was our ironworkers that built the bridge. We admire those men that were up on the bridge, putting it all together.
Out on the structure, high above the waters, in the winds and fog, it's as precarious now as it was for the early builders.
It's miserable. It's miserable. I mean, you have to hang on. You got one hand for the bridge and one hand for yourself.
At best, working on the bridge was miserable. At worst, it's treacherous. But it's the Depression, and work is scarce. Men were queuing round the block for soup, or better still, work. But even at a time when labour was two a penny, Chief Engineer Strauss took pride in the welfare of his workforce. With great foresight, he was obsessed with safety. At the time, it was understood you'd lose one life for every $1 million spent on a construction project. Strauss would not accept 23 corpses as a price for his bridge. He's not only the first to insist on hard hats and safety cables for all, but goes as far as experiments with sunscreens, glasses to stop sun blindness, and even a cabbage-based hangover cure for his hard-working, hard-playing crew. The biggest and most expensive safety measure was a giant net, like the ones used by circus high-wire acts. It was strung underneath the span as it extended out over the water. It cost around $125,000, but it would go on to save a total of 19 lives. A lucky bunch who all became members of the appropriately named and exclusive Halfway to Hell Club. May 1934, and the American flag is proudly flown on top of the completed Marin Tower. A group of hardy souls stand tall on the highest bridge structure ever constructed. 44,310,450 pounds of steel assembled in a maze of hollow segments so complex that men get lost in them. All held together by 300,000 rivets, each one hammered in by hand. Now come the cables, the longest and thickest ever fabricated. Too heavy to be transported whole, they're spun from 80,000 miles of steel wire, shipped over from the East Coast on giant spools. The main cables containing 24,500 tons of steel are spun, a wire at a time, using technology invented by the builders of the Brooklyn Bridge, the Roebling Company of New Jersey. The Cable A-team came up with an ingenious solution to speed up their work. Instead of one carriage to carry the individual wires across the water, they put two on the job. Starting from either end, they meet in the middle and swap wires midway. 27,572 wires bunched into 61 strands of cable were at one point being spun at record-breaking 4 tons of wire a day. The pace reached an all-time high. In spite of Strauss's best intentions, accidents started to happen. On February the 17th, 1937, tragedy struck. A pair of workers were in the famous safety net collecting debris when a platform above them suddenly failed. The 5-ton structure and a crew of 12 men crashed down into the net. It held, but only for a moment. Then it cracked like a machine gun and ripped like a picket fence, splintering. 12 men fell to icy deaths in the waters below. There were only 2 survivors. One, seriously injured, was picked up clinging to a floating corpse he thought was alive. May 1937. With the bridge at last completed, the long-awaited day arrives. The 27th, designated as Pedestrians' Day, sees some 200,000 people walk, run, skate and tap dance their way across the bridge. The following day, a motorcade of official vehicles works their way across the record-breaking span. Joseph Strauss proudly pronounces his bridge open to the world, proclaiming that if it is serviced by generations, it should have life without end. Age 67, having spent the last 20 years immersed in politics, triumph and tragedy, Strauss moves quietly to Los Angeles. Within a month, he is bedridden. Within the year, the man whose vision and determination built the bridge is dead. However, no one doubted the strength and safety of this awesome structure that is his legacy. But within 3 years, something was to happen that changed everything. October 1940, and right in front of the eyes of the world, and to the dismay of the Golden Gate engineers, the 3rd longest and most modern suspension bridge in the world disintegrates in the wind. The superstar consulting engineer who signed off the numbers on the Golden Gate, Leon Moiseev, is the brains behind the bridge's daring new design theory. With the shocking collapse of Tacoma Narrows, all fingers now point at him. Immediately, the Golden Gate Bridge Authority contact Charles Ellis, assistant bridge engineer and the source of their original designs. Ellis painstakingly checks every calculation that was done on the Golden Gate. Amongst other things, he confirms that it was the Tacoma's narrow profile that caused its destruction. The Golden Gate ratio of width to length at 47:1 is positively chunkier than Tacoma's at a slinky 72:1. This, combined with a better wind deflection profile, says Ellis, puts the Golden Gate in the safe zone. Sitting in its own natural wind tunnel with gusts from 20 to 60 miles per hour, everyone at the Golden Gate hoped his theories held up. For many miles in either direction, there is nowhere for the wind swooping across the Pacific to break inland. The gate is that break. As the wind picks up, it becomes a danger to traffic, especially when the bridge is the first thing a winter storm hits after a mammoth journey.
What happens is, like trucks, because they're taller, they get hit by the wind and they have a hard time staying in their lane.
11 years after Tacoma, the Golden Gate faces its own moment of truth. A wind measuring 69 miles per hour crashes through the canyon. With the spectre of Tacoma not such a distant memory, officials close the Golden Gate for the first time in its history. The roadway pitches. The bridge swings. Ellis and Moiseev had designed the bridge to deflect sideways in 90-mile-per-hour winds by an impressive 27 feet. That's a swing equivalent to 3 station wagons end to end. Even today, on a calm day, you can still feel it gently swing, sway, and flex, responding to the wind and the traffic. On some bizarre occasions, the weather can be different from one end of the bridge to the other.
You can be at one end and be in a fog and a miserable weather, and on the other end you can be and it'll be nice and like t-shirt weather. Big difference in the climates between the north side and the south side.
It's this clash of cold and hot air that creates an even more destructive element than the wind. It also produces the signature weather of the bridge and San Francisco itself, the fog. Love it or hate it.
While today is gorgeous, I assure you there are days where from where I'm sitting, it is a total myth that there is a bridge out there because you can't see anything except cold fog.
The cold fog is trapped by the air mass around and will sit brooding over the bridge. For about 3 months of the year, the Golden Gate has its own private weather nightmare, while the rest of the bay basks in sunshine.
It's a lot of fog, a lot of damp. Many times you come to work, we can even see the water. Many days. And the fog is funny, comes and goes. Sometimes we'll go in for lunch and it's clear, or vice versa. It's very unpredictable.
The corrosion of the steel by salty fog is slowly, silently killing the bridge. Keeping on top of the corrosion is a full-time job for the 55-strong maintenance team. They hang out in a secret hollow beside the bridge called the Boneyard. The rolling repairs on the bridge pass through the boneyard piece by piece. Each rotten section is removed and sandblasted back to bare metal. In some cases, like this stair panel, the metal fabric has been eaten by the salty air to beyond the point of no return. When this happens, new sections are manufactured using the old sections as template. These crosspieces are being recut exactly like the originals. They will be primed and finally sprayed in the famous international orange colour. Then they will be fixed out on the bridge to face the fog.
Even underneath, where you would think you'd be protected from the rain, even underneath you'll get that moisture from the fog on the structure, and it's raining on you underneath.
These steel pins that tie the suspension part of the bridge to land have rusted solid. They have to be cut out and remade. In fact, piece by piece, as it rusts away, the bridge is being replaced. Much of what is now the historic Golden Gate is new. The skill of the original bridge builders lives on in the ironworkers of today. The main cables are one of the few sections that remain untouched from the day they were built. The secret is the way they were sealed, way back in 1936. Once the wires were stretched across from one anchor to the other, they were squeezed together with 120,000 pounds of pressure and then cable bands strapped around. They were then coated in rust-proof paint and wrapped in 3 miles of steel casing. They're as sound today as the day they were spun. Today, a section of the cable is a star tourist attraction next to the statue of Strauss. Visitors place their hands on the slice and marvel that strands no larger than a pencil can hold up an 887,000-ton bridge in a 70-mile-per-hour gale. What they don't know is that a destructive force far greater is building in the ground beneath their feet, and it threatens the very existence of the bridge. The threat of a major earthquake in close proximity of the Golden Gate is today more real than it has ever been.
I want to believe that it's not going to be tomorrow. However, it may happen tomorrow.
To give the bridge a fighting chance against the seismic forces, the ongoing repairs have been stepped up. A full tilt retrofit is needed for the bridge to face the music.
Very simply, we're fine-tuning the bridge, just like a piano. We're taking the strings of a piano, the strings of the steel of the Golden Gate Bridge, and we're fine-tuning it to either absorb seismic forces or to dissipate seismic forces. We want them to do one or the other.
To absorb or dissipate the shock of a quake, many sections of the Golden Gate Bridge must be removed, retuned, or replaced. The biggest problem hampering this earthquake protection work is, ironically, earthquakes. As the retrofit progresses, the bridge must always remain as earthquake-proof as possible. With traffic thundering above and people on the bridge 24/7, the rule is that this painstaking process can only happen 2 rivets at a time. If a quake hits and any more than 2 rivets are out at any one time, the whole web of steel could collapse. So rivet by rivet, the bridge gets its new lease of life. No other suspension bridge retrofit in the world is as complex or as comprehensive as at the Golden Gate. Behind every step is the reality that the bay and its bridges have, within this generation, faced a seriously destructive event. At the end of the 1980s, the Loma Prieta earthquake shook up the Bay Area and the lives of just about everyone who lives there.
I went through the Loma Prieta, yes, and that was back in 1989. It was very exciting. Yeah, so anybody who is a geology fan, I think, would have found it quite exhilarating.
All earthquakes are measured on a scale called the Richter scale. Tiny ones called microquakes can only be recorded by seismographs, but anything over 3.5 can be felt by a human. Loma Prieta was 6.9, and everyone felt it. The quake left 14,000 homeless, 62 people died, and around 3,000 were injured. Property damage was estimated at $7 billion. On the day the earth shook, the security officers at the Golden Gate Bridge heard the shockwave as it rumbled through the ground.
I was actually in this office. The noise sounded like a locomotive was driving through the building.
The Golden Gate had never encountered forces anywhere near the level of the Loma Prieta earthquake. Even for seasoned Californians, the intensity was beyond experience.
I've lived here all my life, but I'd never been involved in an earthquake that strong, and I'll never forget it.
The infrastructure of the Bay Area took a serious beating. In Oakland, 1.25 miles of the upper section of the Cypress Viaduct on the Nimitz Freeway collapsed. 42 people were killed, crushed to death in their cars on the lower deck. To the north, a 30-foot section of the Bay Bridge, built at the same time and by many of the same workers as the Golden Gate, collapsed in on itself. On the evening of the quake, at the Golden Gate, the bridge began to sway. This is the invitation that the then chief engineer Dan Moan has been waiting for. He got in his car and began to drive across it.
At the height of the earthquake, I was right at the center of the main span. I was driving my car, and my first impression when the earthquake started was, doggone, I've got a flat tire.
Dan is feeling the initial shake from the quake. That's 75 million pounds of dead weight on the move. As the shock transfers through the structure to the roadway and the cables, they begin to absorb the forces by moving.
So you can see the suspender rope start vibrating quite rapidly, and then we knew for sure it was an earthquake.
Although the epicenter is in the mountains of Santa Cruz, most damage is in the urban areas of Oakland and San Francisco. But at the Golden Gate,
you could visibly see what we call the suspender ropes, the smaller cables that are coming down that hold the roadway up. You could actually see them. They were swaying like that back and forth, noticeably from here.
The bridge is doing what it was designed to do. It sways, shock absorbing the forces of the quake, then releasing them through vibration and movement. The dissipation of energy saves the Golden Gate from disaster and is the all-encompassing theme of today's retrofit. Absorb or dissipate the energy, and you'll stay in one piece.
We had no structural damage, just little housekeeping work. That's why suspension bridges by nature can withstand earthquakes better than a rigid structure.
This is a rigid structure. Its collapse results in tragedy. Although the Bay Bridge, which is part of a $2.5 billion retrofit program, was 50 miles from the center of the quake, it felt the shockwave and cracked up. On the Golden Gate Bridge, the designers knew the roadways should move, under traffic load, in wind, and of course, earthquakes. The expansion joints either end of the span allow for this. But unfortunately, recent testing on the bridge shows it's not going to be enough if history repeats itself. 1906, on an April morning, the blossoming city of San Francisco is shaken apart by an earthquake. It tears a 290-mile gash in the Earth's surface as two sections of California slip in different directions.
So what occurred in 1906 was two continental plates moving, and suddenly moving very quickly at a distance of probably somewhere between 16 and 25 feet in 40 seconds. So that's massive. That's like earth surfing.
There is no warning. It's all over in 40 terrifying seconds. People are killed in their sleep by falling debris. Fires break out, started by jets of flame from the ruptured gas mains. It's thought that 3,000 people are killed. Some bodies are never found. Over 28,000 buildings are destroyed, and half the population is homeless. A massive 7.9 on the Richter scale earthquake, large enough to be detected all over the globe, wipes out San Francisco. If the Golden Gate Bridge had existed when the 1906 nightmare struck, it may well have ended up in the bay. Today, detailed studies reveal how the bridge sits between California's two most active earthquake fault lines, the San Andreas and the Hayward. Each fault is the edge between two chunks of the Earth's surface. These continental plates that crisscross the planet move all the time, but not together and not in the same direction.
And after a period of about approximately 250 years, the areas where the continental plates are caught are going to fail. And what happens is they don't just shatter. What they'll do is they'll release every ounce of energy they stored when they were much larger.
In 1906, it was a phenomenal amount of energy. It rates as one of the most significant earthquakes ever, and along with the Loma Prieta, it has generated a wealth of seismic knowledge. Unfortunately for the Golden Gate Bridge, that knowledge has led the scientific community to a frightening certainty. Another earthquake larger than the Loma Prieta and the same or greater than 1906 is on the way.
I think it's a certainty. We don't know when and how long it will be, but there's a certainty of an earthquake on the San Andreas Fault that will produce motions here much, much greater than produced by Loma Prieta earthquake.
With today's seismic and structural understanding, the smart money reckons that in order to stay standing, the Golden Gate Bridge urgently needs a serious upgrade. The two key new technologies being enlisted are isolation bearings that separate sections of the bridge and absorption devices to take the force of the earthquake and hopefully spare the structure. The retrofit is complicated and expensive, but there's nothing better than feeling your own earth tremble to convince you to get on with it.
It's one thing to think about them theoretically. It's something else to wake up in the middle of the night with the bed shaking and the windows rattling and wondering whether or not the roof's about to fall in. My commitment to seismic retrofitting became much, much more personal after my first earthquake was experienced.
So how can a retrofit, unlike anything done on a suspension bridge before, save the Golden Gate from the next big one? The 1906 earthquake is the most destructive in US history. At today's prices, it cost California $8 billion. What the scientists predict is that an earthquake the same or larger is on the way. For the 70-year-old Golden Gate Bridge, it's very bad news.
It may happen tomorrow. It may happen in 10 years. But one thing we know, it will happen.
And when it does, the bridge must be ready. But how far can you go, and ultimately how strong an earthquake should you be prepared for?
The state hired professionals to determine what is the maximum credible earthquake, and that's an 8.3 earthquake.
An 8.3 earthquake is catastrophic. The Loma Prieta was a 6.9 and it killed over 60 people and cost over $10 billion. The energy released by an 8.3 is the equivalent to the detonation of over 3 billion tons of dynamite. That's a serious hit for any structure.
And if it's anything worse than that, we really don't need to worry a whole lot about the Golden Gate Bridge because I'm not sure all of Western California will still be around.
The retrofitting is based on the heart of the earthquake event, the epicenter, being in the bridge's own backyard, just 7 miles west on the San Andreas Fault. The engineers must retrofit for what's called the maximum expected event from this nearby fault.
Now, of course, they're retrofitting for a magnitude 8.3, which is maximum expected event from that fault.
The maximum expected event is a curious cutoff point. What it actually means is, at what point does it become a waste of money to fix up the bridge to survive an earthquake? In the case of the Golden Gate, that's a lot. It's the most complex and costly earthquake-proofing project ever undertaken on a bridge. In fact, if it were any other bridge, the best thing would be to knock it down and start again. But the Golden Gate isn't just any old bridge.
If you talk about important structures in America, we talk about the Statue of Liberty and the Golden Gate Bridge.
It's without doubt the most recognizable bridge on Earth.
That's awesome. I think that every engineer that has ever worked on a bridge has a very deep feeling about it.
It's an artery that carries almost 40 million vehicles a year to the north and south of the bay. At $5 a return trip, the traffic brings in over $84 million a year in tolls. Sounds like a lot, but that money isn't even enough to keep up with the regular maintenance, let alone find the mega cash it's going to take for the retrofit. A short drive across the Bay Bridge in Berkeley, California Transport are also putting earthquakes at the top of their agenda. Caltrans are super focused on seismic forces. They have to be, ever since the Loma Prieta quake took out so much of their infrastructure, including the Bay Bridge itself. They're testing ways to absorb and isolate the seismic energy from an earthquake. To do this, they make their own quakes. This is the largest shake table in the USA. It can simulate every earthquake that has ever been measured. These are the hot new bearings destined for the Golden Gate Bridge. They're the devices that should keep it standing into the next century. They're rubber with a lead core and are designed to be placed at points on the bridge where the seismic movement on one section needs to be isolated from the other. And that is the secret of the retrofit. Section by section, preparing the bridge to go with the seismic forces when the ground beneath begins to shake. The work will take over 20 years and is writing the book on retrofitting suspension bridges. Here at the spanking new North Approach Viaduct, they've already installed the rubber lead isolators. At the North Tower, they've put in stiffeners and strengthened all the joints, and at the pier below, they've studded it with pre-stressed steel bars for extra strength. With Phase 1 complete, they've turned to the south. Here they'll be installing more seismic isolators, replacing the towers and all the metal bracing. The Fort Point Arch, built to carry the bridge over an old Civil War fort, is a particular challenge.
Right behind me is the Fort Point Arch, and in our computer modeling, when we did our seismic analysis, it shows that that arch can rock and actually rise up and potentially collapse and rock out of its position.
Studies revealed that the whole arch, pulled up by the cable, lifts off its foundations in an earthquake. That's fine, because the movement would absorb the quake's energy. But it must drop back precisely into position when the dust settles.
So what we're doing is we're going to control the movement of that arch by strengthening the steel within it, and also by putting energy dissipation devices between the pylons that surround it, the two concrete pylons on either end. So it will be redirected back onto its footings if it begins to rock during an earthquake.
Meanwhile, on top of the world where the 887,000 tons of the bridge hangs over the two 3,000-ton saddles, the retrofit will strengthen and immobilize excess movement. Dampers will be installed where the tower and the roadway meet, and parts of the concrete fender that's in the water will be replaced. Although this is a race against time to beat the next earthquake, the whole high-tech process has one major fly in the ointment. it's the most technically challenging of all.
It would be very simple just to come and redo everything and change its appearance, but at the end, there will be no more of the beautiful Golden Gate Bridge.
When the day is done and the retrofit complete, no one must ever know it's been touched.
It's funny to say it after we're spending all these millions of dollars, but we really have to make it look like nothing happened.
Every rivet has been checked, over half the steel has been replaced, the concrete towers are reclad, the roadways and the cables it hangs from are all new. Bit by bit, the bridge is being totally replaced. Ultimately, there'll be nothing left of the original steel and concrete that took lives, made reputations, and became a stunning monument to progress and beauty. But after everything it's been through, it remains the Golden Gate, the most famous, most admired bridge in the world.
I've heard people say, you know, I've saved money my entire life so that I could come see this bridge.
First time round, it was a groundbreaking engineering marvel.
Our day is coming, and we're just racing against time to get that bridge retrofit so it can be saved forever.
Second time round, the mother of all bridges is being given a new lease of life. The Golden Gate Bridge has weathered the past, and if the earthquake fix is done in time, has many golden years ahead. But nature waits for no one.